So good morning or afternoon, wherever you all are. I can see there's people from a wide range of places across the globe joining us this morning. I'm Thomas Neeson, I'm managing partner at Cundall, and my job here is just to really introduce the speakers to you on our topic today, which is residential overheating. Obviously, this development of residential has been big on everybody's agenda, and now with everybody spending 100% of their time in their residences trying to work, it's obviously become more of a topical issue in terms of how do we design residences for the future and homes that are going to be suitable for not just living in, but also working in, and maybe working more flexibly in, as everybody's trying to adopt those ways of working where they can. We're obviously meeting in very challenging times through COVID, but one day this will all be over. We'll be getting out of it. Thankfully, the peak seems to be passing in most countries. And we will get back out to doing our day jobs and working on delivering projects in the built environment, and probably with a very different thought process than we've had before now, or a more maybe accelerated process in terms of developing sustainable designs, which is what we've always been all about, regardless of the building types we're working on. But there'll be a whole lot of new design parameters and factors to take into account going forward. So over this is the fifth out of six webinars we're doing. Over this 6-week series, we've been looking at different aspects of sustainable building design, and we'll go on beyond this to cover a series on driving towards net zero carbon in the next series of webinars that we'll do. As I said, sustainability is at the core of everything we do in Cundall, and we look at 4 cornerstones of how we can impact the sustainable world, and that is in our homes and communities, in our workplaces, the places we go to work at and you go to work at, in all of our projects, and then in providing industry and thought leadership. And that's today's session is one of those events where we're here to try and pass on some information, educate people, but very importantly, gather your thoughts and questions and your ideas, so together we can build knowledge that will benefit all in the work that we do. Today's presentation will be about 30 minutes. The presenters have packed a lot of slides and information in that they'll try and disseminate to you. We've got a Q&A box and a chat box on this webinar, so please ask questions and put forward your ideas, and we'll gather together at the end and have a Q&A session. Today's speakers are Oliver Watts and Matt Hayden, working in tandem because they work on tandem in lots and lots of projects, because they have complementary and conflicting skills and disciplines that they bring to bear on lots of these projects. Oliver's a building physicist and sustainability specialist, and he really gets under the skin of how buildings work and how we create the internal environments that are going to deliver both good human comfort and sustainable operation and sustainable performance in operation. Matt's an acoustician, and he was one of the lead authors on the recent Acoustics, Ventilation and Overheating Guide, which is very relevant in today's market. He's also vice chairman of the ANC Good Practice Committee, and he spent most of the last 5 years specialising in assessment of noise impacts from building ventilation and how it relates to building overheating. So these two will look today at what was current, what the future might look like post-COVID, and all the things that we'll have to design and consider in the future to create the buildings that everybody wants to spend their lives in. So without any further delay, I'll hand you over to firstly Oliver and then Matt, and then we'll get together at the end for some questions and answers. So enjoy the webinar. Thank you.
Thank you, Thomas, and welcome everyone. Before we dive right into the topic today, just brief overview about who we are as Cundall. So we are 950 people strong. That's across 25 global offices. Well, currently it's about 950 unofficial global offices. And what we're really proud of this particular year is that we are aiming to be net zero carbon operation. In terms of our locations, this map illustrates kind of where we operate and where our offices are based. So the darker blue is where we have our offices, and the lighter blue is where we've got active projects and we're working in. So real global team. and that means we can pull on resources and specialisms and best practices from all over the globe, and deliver them on projects here and there. In terms of our services, we have 4 core engineering services. We are an engineering practice. So they are the building services, civil engineering, structural, and then sustainable design. But under that umbrella, we also have specialists such as our acousticians, our air quality, security, transportation, that all feed into kind of one holistic engineering solution in delivery on projects. In terms of the sectors we work in, the broad brush across most of the sectors in terms of development, from aviation, transport, healthcare, looking things at master plan level, education, and of course residential, which will form the basis of our focus during today's discussion. So overheating in the residential setting, why do we care? Why should we be concerned? What are we looking at today? Well, 90% of our lives in a typical year we spend inside, and of which 65% is spent at home. Now, recently, and those numbers are going to be much nearer 100. However, we think the fallout from COVID is that the demands we place on our homes are going to change. So no longer is this somewhere you retire to at the end of the day. These work practices are likely to mean that a lot more people are looking to work from home, a lot more flexible lifestyle. That means that what we demand from these spaces in terms of comfort and usability is changing and can influence how, and we should influence how we are designing. The growing trend is obvious. We're seeing globally average temperatures increase already by 1 degree. Here in the UK, 9 out of the 10 hottest years on record have occurred since the millennium. And just last year in Cambridge, temperatures were recorded at 38.7 degrees, setting a new high for the UK. So what does this mean? It means that obviously the external temperature influences what we experience internally, and increasingly we're seeing reports of mid to high 30s and even 40 degrees being experienced in the residential settings. That's both living rooms, dining rooms, kind of corridors. And what an interesting study came out from the UK's Committee on Climate Change, highlighting that 20% of residential homes are prone to overheating, even in cool summers. So that's excluding kind of heat wave events. So this issue is really out there, and is coming to light in a lot of people's homes. So what do people do to address that? They seek comfort, especially if it's not well designed. This comfort can be sought in kind of quite dangerous ways. We've seen on student residential accommodations, students sleeping in the corridors, accessing flat roofs that they shouldn't be, just to seek this comfort. And yes, you can joke and make light of it. However, it is more than just a comfort issue. It's also a health issue. The heat wave events across the globe have caused many deaths. In 2018 in the UK, 900 deaths were attributed to the heat wave events, and across Europe, in particular France, last year, over 1,500 deaths were reported as a consequence of the heat wave events. The majority of those are in the elderly, and the 75 plus was 50% of those statistics, unfortunately. So what are the causes of this overheating in the residential sector? Well, increased urbanisation is probably the main driver. The drive for development in inner cities, for people to live close to where they work, means that we have increased population densities, higher flats. This all contributes to the urban heat island effect, with the increased amount of concrete and the darker surfaces. We're also looking to develop on more blighted sites that previously we might not have considered for residential use, but now the value of the residential sector is such that these sites are becoming economically viable, and we need to be designing them to still provide the comfort as well as the carbon and energy efficiencies that we desire. There's also issues with installations, insulation not being installed properly, the controls, looking at vent strategies, kind of how they marry up, and how they the difference between the intended design and what we're seeing in practice. But that's saying, it all comes down to the crux of it is the design. What we're seeing is kind of two major influencing factors when we look at overheating, is too much glazing and insufficient ventilation. And the other kind of area which is often forgotten in the homes, or particularly in blocks of flats, is the kind of communal corridor areas, where they're often landlocked because you want you want the windows to be in the occupied spaces. That's where the value is for daylight. However, we often see hot water pipe work running through these spaces, the internal heat gains building up, and it's often a cause for discomfort and complaints among freeholders and landlords. I mentioned that too much glazing is often the root cause. Here at Cundall, our focus is on how can we optimize a facade in terms of it, both energy, thermal comfort, and daylight. So looking at window to wall ratios. As a kind of starter for 10, we'd always advise looking at a kind of 40% glazing ratio compared to solid wall. That's taken from the inside. However, there's a lot of factors in play, such as external shading, any coatings to the glass to kind of block out the solar gains, and also where we position those windows on the facade. So are they kind of floor to ceiling, or are we looking to push them up as high as we can to the soffit to maximize the daylight penetration to a particularly deep hand space? And then the other factor, and kind of one I want to draw attention to, is ventilation, and what we mean by ventilation in the residential setting. We look to break it down into three component parts. These are the minimum fresh air, purge ventilation, and then your overheating strategy / ventilation. When I mention minimum fresh air, what I'm referring to here is kind of your background ventilation to go about your day-to-day activities. So your natural breathing, your removal of CO2, any moisture content, manage humidity, odors, all in play. That kind of this should go on the background as you go about your daily stuff, daily lives. And just to illustrate this, that the blue bar on the screen now is the kind of required fresh air requirement. And traditionally, this was achieved through trickle ventilation and the ventilation rate we get through infiltration. Now, as building regulations have proved, and as the standard of construction and a drive for a more airtight, firmly sealed building, it has meant that the infiltration air exchange we receive has shrunk dramatically, and that means there's kind of a surplus. There's not a surplus. Sorry, there's a requirement there for additional fresh air. And the solution we're often seeing, and from an energy point of view as well, is an MVHR system. So it's either a centralized or a local system, which will provide this background ventilation. And the building regulations dictate the air volume and the air exchange that's required. And this is also the energy. This will be providing it throughout the winter and summer. The second aspect of ventilation I want to highlight is the requirement of purge ventilation. So this is when you require rapid dilution of internal pollutants. It's often when the internal conditions are worse than external, and is usually typically a short duration. So for instance, if like me, you've cracked on with some DIY while we've had extra time at home, you end up slinging the windows open to allow that ventilation to remove those VOCs and that smell, because the internal environment is unpleasant. In terms of the building regulations in the UK, there is a requirement that an open vent of equivalent to 5% of the floor area is required. So where we see designs that say sealed windows, they still need to have this 5% openable area, so that occupants can sling open their windows for those limited scenarios throughout the year. The other option is to look at it mechanically. However, the duct sizes associated with this is a vast uplift and not something we typically see in the residential sector. And it's not often we go down this avenue. It causes a lot of issues with ceiling void depths, which in turn impact the floor to ceiling heights, which in turn impact the daylighting of the space. And to kind of adjust for that, you're looking at adjusting building heights, and it can all lead into the viability of the scheme. So we would always look to prescribe purge ventilation through an openable window or a ventilator of some sort, a passive measure. Overheating. So what are the sources of overheating? We're probably all fairly familiar with this. The kind of the external air temperature is a huge factor. Also the solar gains. So those gains that we're highlighting with the heavily glazed facade will be a lot higher. Orientation will also influence that, but also what's internally in a space. So we as people give off a lot of heat. Some give off a lot more hot air than others. And also the equipment in those spaces. So from cooking or just our small plug-in equipment. And what's worth highlighting here is if we do move to a more flexible office-based home working situation, are we likely to see more equipment gains in those spaces? Yes, we're likely to bring in 2 monitors for home that previously we might not have had before, and all adding to the kind of internal heat gains. So in terms of the building regulations, there is no requirement currently to undertake in the UK any overheating risk assessment or any assessment regarding overheating. Local authorities are cottoning onto this, and there are a lot of requirements in London, Manchester, that all dictate that you should demonstrate how you've designed out the risk of overheating. And the commonly used practice for the residential setting is CIBSE TM59. CIBSE TM59 is built on 2 criteria principally, one looking at daytime and the other looking at nighttime. So at daytime, it's the number of hours, number of occupied hours where the temperature inside is greater than 1 degree than the temperature outside should not exceed 3% of those hours. At nighttime, particularly just bedrooms, looking at the internal temperature should not exceed 26 degrees for more than 1% of the annual hours. Particularly in the kind of the south of the UK, the nighttime criteria can be particularly challenging, where we've got west-facing bedrooms with a large glazed area and limited shading. They're kind of influenced by the low-setting west-facerly sun, and that means that any external shading also doesn't tend to block this out. The other thing worth noting is that the weather files prescribed of the kind of standard weather files for this year, the peak is only 34.6, and if you think back last year in Cambridge alone, we witnessed 37.8. So you could stress that we need to go even further, and there are weather files that allow for future climate change scenarios that can be reported, but often these are not requirements to achieve. So how do we address that? Well, I've kind of lifted the GLA's approach and their cooling hierarchy, but this can be applied on all projects, all globally. So the kind of first priority is to reduce the amount of heat entering that space in the summer. So I've already mentioned looking at our glazing to wall ratios, but any external shading, any coating specifications on the glazing, but also the building fabric itself, so our insulation levels. So we limit that heat entering the space. The second aspect would be to minimize that internal heat generation. So yeah, looking at equipment gains, can we look at low energy lighting, looking to limit the white goods equipment we're putting in, specifying energy efficient equipment that won't contribute to the heat in the space. And the next step is looking at how we manage that heat in that space. So through use of high ceilings, increasing the volume of a room, but also can we have exposed ceilings? Can we use the thermal mass of a building to help manage and overcome some of the overheating risks we're experiencing? The next item and the kind of the key step, and this is where the conflicts come with myself and Matt, is the use of passive ventilation. So by that we mean kind of opening of windows or ventilators to provide the necessary volumes of air exchange to maintain temperatures at a comfortable level. For this, we would tend to say that in the warmer parts of the UK, we aim for window openings that are equivalent to 5% of the floor area of the room they're in. But that can go up to nearing 10% in London and can be lowered as we go further north. However, please mindful that we should be designing for kind of future climate change scenarios, so that provision should always bear that in mind, given the life cycle of the building. You can also look at mechanical ventilation systems to support this. However, as I've kind of illustrated, these would be typically a lot larger than what you see just to do the background ventilation, and we see them as more of a supporting aid alongside some passive measures. And then the final step is looking at active cooling, and this is where kind of the last resort on the hierarchy, where perhaps we're limited with our passive ventilation capabilities. Maybe there's certain window restrictors for security reasons, the air quality issues, and of course noise considerations locally. And it's on that note I will hand over to Matt, who will kind of highlight some of the passive options we have. Matt, I think you just need to take yourself off mute.
Thank you, Ollie. I made a bit of an early start there. So hello, I'm Matt, and I'm going to talk about the link between acoustics and noise and overheating. But before I start, acoustics is really important, but air quality is also a really important issue here as well. And we haven't got time to talk about that today. But if you have any questions, please do try them at the end regarding air quality. And if Thomas, Ollie or I can't answer them, we'll pass you on to Glyn Hodgkiss, who leads our air quality team here at Cundall. So as Ollie mentioned, the normal way to cool a building down and avoid overheating is to open a window. But when you open a window, you not only let in cooling air, you also let in noise and pollution. And the problem is that on many residential projects, overheating, noise and air quality get looked at separately. So often, a new development will require a noise assessment. So an acoustic consultant will go and do a survey, and they'll write a report probably for planning, saying, yep, everything's fine. As long as your windows are closed, the noise levels inside your new residential development will be good. And then separately, a mechanical engineer or building physicist will do an overheating assessment, potentially in line with TM59, as Ollie talked about. And that might say, yep, your building won't overheat if your windows are open. And these things obviously clash. And there was some quite interesting research done. This was carried out in 2017 and looked at a number of, I think about 152 large developments, residential developments in London. All of these developments achieved planning permission. And the review found that of these 150 developments, about 122 of them had a planning noise assessment and had an overheating assessment done. And of those 120-ish sites that achieved planning permission, remember, 100 of them had a noise assessment that said everything's okay if the windows are closed, and an overheating assessment that said everything's okay if the windows are open. So this clash is not being spotted by planners, and it's being missed by the design team as well. And if a building continues to be designed on this basis, you'll end up with a building where the occupants have to choose between it being too hot and too noisy, and it might not be fit for purpose. And this problem is only going to get worse. As Ollie mentioned, the world's getting hotter. We're also running out of quiet sites to build residential buildings. And current conditions mean that we're currently spending a lot more time in the house. And potential future changes in work patterns also mean we could be working from home more. And if people are in the home more, they're going to be exposed to these problems more. I'm now going to try and do a little sound demonstration to give you an idea of the performance of an open window and what the effects might be. And we normally do this in a more controlled environment where we can fully control the level of noise and say this is 60 dB, this is 70 dB, that sort of thing. But today, as you're all listening on different devices and through headphones and things, it's going to be a more rough and ready relative type assessment. So if you can, ideally, if you don't touch the volume during this assessment, because it's what I'm trying to show is just the difference between levels. So firstly, I'm going to play some relatively loud traffic noise. The level will depend on how loud your speaker setup is. And if you can imagine, this is the level of traffic noise outside a residential property on the pavement. So this is outside, adjacent to the road. So hopefully you could all hear that, some traffic noise and maybe a motorbike going past. I'm going to now play you the same sound, the same sound bite, but this time the level's been reduced to reflect what it would sound like if you were inside a typical residential apartment with some fairly standard double glazing and windows closed. So this is going to be about 25 to 30 dB quieter, but that will vary a little bit depending on how you're listening. So how much of that you can probably hear does depend on what your volume settings are. But what I'm trying to show is that even with fairly standard double glazing, you get quite a good reduction in noise from outside. And with the windows closed, if you need to get more noise reduction, you can just increase your glazing specification. Next, I'm going to play the same sound clip, but this time inside a room overlooking that road with the windows open. And a partially open window will typically give between 10 and 15 dB of noise attenuation. And that's what you'll hear now. So hopefully that one should have sounded more similar to the first clip. And I'm probably telling you something you already know here, that an open window is a hole in the wall, and a hole doesn't provide much sound reduction. So if it's loud outside, when you open the window, it's going to be pretty loud inside. So that sort of infers that if you've got a noisy site and you need to open your windows a lot to provide relief from overheating, open windows might not be the right solution. So I'm going to briefly talk about the effects of noise. So noise can be annoying, it can be disturbing. If you're working at home, like a lot of us are now, it can cause task disturbance, and it can also cause sleep disturbance. And these are all unpleasant effects, and they can make people irritable, unproductive, and tired. However, the effects of noise are not just only short-term. If you're exposed to increased levels of noise for long periods of time, they can result in serious health effects. And these include increased blood pressure and an increased risk of heart disease. And people are able to adapt to noise to some extent, slightly more so during the day when you can move to a different room, put headphones on, open and close windows, that sort of thing, but less so at night. But even though you can adapt to noise, the health effects still happen. So to illustrate this, I've just got a little graph here showing a typical 8-hour sleep cycle for a relatively healthy, normal person in a relatively quiet room. At the top are your lighter sleep stages, and down the bottom are the more restorative, deep portions of sleep. And you can see how people have some light sleep, dip into the deep sleep for a bit, then half wake up again, dream a bit, back down to the deep level, and that happens throughout the night. If you sleep in a noisy room, after a while you may be able to adapt and actually get to sleep. But if you're sleeping in noise levels significantly above those, which we'll come on to in a minute, it's likely you won't ever reach those deeper levels of sleep. You'll be staying at the stages 1 or 2. You're basically getting a poorer quality of sleep, and if you're getting poor quality sleep for a long period of time, that will result in significant health effects. So in terms of criteria, noise inside dwellings is not covered by the building regulations, and it's normally controlled at the planning stage, as we mentioned earlier. And most buildings will receive a planning condition, residential buildings in the UK will receive a planning condition based on BS 8233 or the World Health Organization guidelines. And that'll typically be something like 35 dB during the daytime in living rooms, and noise levels not exceeding 30 dB at nighttime, with maximum noise events probably not exceeding around 45 dB. However, these guidelines are not really applicable to the overheating condition. These are aimed at constant year-long averages, these noise levels, whereas overheating happens for different periods of time in different dwellings. And until recently, there wasn't any guidance at all, and definitely no quantitative guidance on the relationship between noise and overheating. But in January 2000, this year, we released the Acoustics, Ventilation and Overheating Guide. This is an ANC and IOA document, and I was one of the authors of it. And one of the key bits of this document is what we call the AVO graph. So there's quite a lot of information on here, but what it's essentially trying to say is the noise impact doesn't just depend on how loud things are, it depends on how long or how often you're exposed to that noise. So if your dwelling only rarely overheats and you only occasionally need to open a window, it might be okay. You might be able to tolerate quite high levels of noise for those few days or few weeks of a year. However, if your dwelling overheats regularly and you have to have the windows open for most of the summer and lots of evenings in the summer, you're unlikely to be able to tolerate very high noise levels at all. And they'll probably be very similar to that 35 and 30 we talked about before. So when we're designing a residential building for acoustics, you don't only need to know how loud it is going to be inside, you also need to understand the overheating and ventilation strategy. Therefore, it's essential that we carry out holistic design, that we work with other people. We need to work with mechanical engineers, building physicists, air quality consultants, the architect, and the client. So if you have an overheating problem or a noise problem or a mix of the two, what can you do? I'm going to now look at some passive mitigation options that can allow you to control overheating whilst controlling noise. You can, in inverted commas, solve the noise issue by using mechanical cooling or air conditioning, as Ollie mentioned before. But here at Cundall, we see that as a last resort, and we'll always try and use a sustainable passive solution where it's possible and appropriate for the development. So we've briefly talked about this before as well. The normal solution is open windows, but as we've seen, they only provide 10 to 15 dB of noise reduction, which isn't that much. So if you've got to have them open a lot of the time, they're probably not suitable for controlling overheating on noisy sites. But one thing that often gets missed on open windows, in the UK, people generally use an assumption that an open window will reduce noise by 13 dB. But in reality, the type of window you use can have a big impact on how much noise is reduced. If you have an open sash window, which is effectively a hole directly overlooking a busy road, you'll probably only get 8, 9, 10 dB of noise attenuation. Whereas if you had, for instance, a side hung window, like shown in the image on screen now, and if the noise source was located to the left of that window, so the opening light actually acted as a screen, you might get somewhere near to 20 dB of noise attenuation. And this might mean, through clever window design, you can use open windows on a scheme that on an initial glance might have looked not possible. Another option would be windows that are specifically designed for acoustic performance. And you can get acoustic reductions from outside to in of around up to 25 dB with this type of solution. But there aren't many of these things being used, and they're not commonly used at the moment. And the attenuation you get really depends on the design. But here are a couple of examples of what this might look like. One example would be an acoustic winter garden. So here you have offset ventilation openings, and you might include an acoustically absorbent soffit or ceiling in that winter garden. So it acts like a big silencer basically, and you might get 25 dB noise attenuation out of something like that. Another option would be a barrier acoustic window. Again, 20 to 25 dB noise attenuation might be possible with this type of solution. But as you can see from these images, both of them are likely to significantly affect how a facade might look and also impact on internal areas. So they need to be considered very early in the design if this is the sort of thing you want to use. Another option that is a little bit more widely used are acoustic louvers. So acoustic louvers can achieve up to 25 to maybe even 30 dB noise attenuation. And the performance acoustically depends on the depth of the louver, the type of noise source. And again, they do impact on how your facade looks. Here's a little image showing the type of system I'm talking about. Externally, there'll normally be a grille covering up the louver, so birds and things don't get in, and leaves. And then internally, the louver will live in the depth of the facade to give the acoustic performance. And then you'll have some doors that can either be manually or automatically opened to control overheating. And that'll let the air in whilst hopefully controlling the noise. And they are potentially a good option, acoustic louvers, in some situations. But one of the drawbacks to an acoustic louver is the acoustic performance is inversely proportional to the aerodynamic performance. So the more noise it stops, the more air it stops as well, which isn't great. So if you wanted to achieve about 15 dB of noise attenuation, you could probably achieve this with a very basic 300mm acoustic louver. And this is quite aerodynamically efficient, and you might be able to get the amount of air required to control overheating into a typical living room or bedroom with the sort of scale of louver shown at the top of those 3 images here. If you wanted to achieve maybe 20 dB of noise reduction, you'd probably still achieve this with a 300mm deep louver, but to get the increased acoustic performance, the aerodynamic performance is reduced. So you'd need a greater area of louver on that facade. And if you want to get up to 25, maybe even 30 dB attenuation, you're probably looking at a 600mm deep louver, which is a lot of space. And it's also very aerodynamically inefficient. And most of your facade might need to be louver to get the level of air into the room to provide that cooling effect. But some of the best ways of reducing acoustic impacts are non-acoustic mitigation measures. So of those measures that Ollie talked about, solar shading, ceiling fans, exposed thermal mass, anything that reduces the amount of time a building overheats will reduce the amount of time windows need to be open, meaning that open windows can be used on sites that are louder and more often. As a sort of rough rule of thumb, open windows might be acceptable on sites when external noise levels during the day are around 58 or below and 50 at night, but this will depend on how often the building overheats. If you're using things like acoustic louvers or specially designed acoustic windows, noise levels up to around 65, 70 during the day and 60 at night, this might be achievable. But if your external noise levels are up to 70 dB or higher and 60 at night, a passive system will be difficult, and it might be a mechanical solution that's required to avoid significant noise impacts. So in summary, open windows don't provide that much outside to inside noise attenuation. So they're not necessarily suitable for providing relief from overheating on noisy sites. But one thing to remember is on most sites, even if there is a very noisy facade, the back of the building's often much quieter, and open windows might be acceptable here. There are passive design options that can control noise impacts whilst allowing relief from overheating to be achieved, but they can impact on the design, especially the facade design, so they need to be considered at an early stage of a project. And I suppose the main conclusion is that noise impacts during the overheating condition should not be considered in isolation, and the best solutions will often include acoustic mitigation and appropriate design to reduce overheating. So that's nearly the end, and I'm just going to play a short animation now that's going to summarize what we've talked about, and then after that I think we'll have a Q&A session.
Overheating can cause major issues in residential dwellings, particularly at night. Several new developments have reached internal air temperatures in excess of 30 degrees centigrade and, in extreme cases, over 40 degrees centigrade. This causes significant occupant discomfort and, worse still, a public health risk, particularly for elderly and vulnerable people. In many modern buildings, when the windows are shut, it is too hot. When the windows are opened, it is too loud with poor air quality. Solutions are possible, but coordinated and holistic design specific to the site is vital between building physicists, mechanical engineers, air quality consultants, and acoustics consultants. Depending on the site location and surrounding environment, our solutions can include openable windows where the air quality is acceptable and the surroundings are quiet, specialist acoustic windows to limit noise, or acoustic louvers, assuming sufficient ventilation can be achieved. Ceiling fans can significantly improve comfort levels, particularly at higher temperature. But in extreme cases, mechanical cooling may be required. With the appropriate combination of these and other options, our designers can provide the right solution for your site or development.
Brill, thanks, Matt. We'll quickly run through then some of the questions that have come through. So the first one was in regards to, I think, the intro slides. Do we have any more data regarding Cundall's net zero in operation? Is this a market-based solution, PPA, or on-site? I will just jump in quickly and say that we are running a number of webinars in the next couple of weeks that will look at the net zero work that we are doing. So keep an eye out for them if anyone's got anything else to add.
Yeah, I'll jump in there. So that was So that's a common question whenever anyone declares themselves net zero carbon. It's how are you doing it? What are the ways? Are you using offsetting? Here at Cundall, we have set out our roadmap 5 years ago, and one of the key targets was this net zero carbon for our operations in 2020. And we have looked to limit our consumption through undertaking materiality review, identifying where we are consuming a lot of carbon and what we can do to limit it in practice. Of course, getting it to zero, we are a business, we consume energy, we consume carbon. So we are looking at offsetting measures and PPA agreements. Our Australia office is the back end of last year, they were certified as operational carbon zero. But that is through the use of offsetting schemes for the very kind of last portion of our offset of our carbon. With the UK looking to follow suit this year, I think we're likely to try and publish some more information in June regarding that. I don't know, Thomas, if you're aware if we're publishing further details.
Yeah, sorry. Yeah, we were aiming for that for summertime. Obviously, things have been disrupted slightly in terms of our information gathering and the like with the current situation, but we're well advanced on it in terms of we have actually published, 7 steps to achieving net zero carbon in buildings and our own operations. We're having a constant review on how do we bring our operational carbon back to net zero. I think people need to, and I guess many people will understand the difference between net zero and zero, being a benchmark level that we've got to get to. So yeah, look out, there'll be more of that in the presentations that are coming in June and on through the summer. Yeah.
Great, thank you. How many schemes have Cundall designed with dual MVHR in market resi schemes?
They having an MVHR system is I'd say is common practice at the moment. We purely from the energy efficiency side, the drive for through building regulations, but also client side to design energy efficient homes. So the MVHR solution is almost a given now on most proposals. Purely there for predominantly the winter setting to look to recover that energy we're putting into a space and not just kind of dumping the fresh air and having to heat it up again while we're kind of exhausting warm, dirtier air. So yeah, I'd say the majority of our proposals, particularly where there are stricter energy efficiency requirements, will have a MVHR system coupled with hopefully an openable window system or natural ventilation system for overheating ventilation.
Yeah, because we have seen schemes that have been asked to come and review and comment on where MVHR was installed in the anticipation that would also, apart from providing ventilation and heat recovery, would control temperature. But yeah, you're not getting the ventilation volumes through these standard systems to allow you to do that. So as Oliver said, you need to open windows or purge ventilation to achieve all of that. Yeah.
Okay. On one of the earlier slides, it's noted that acoustic and air quality can be ignored for purge vent. Can you elaborate?
Yeah, I'll mention about that one. From an acoustic perspective, because purge ventilation happens so infrequently, and when it does, you're normally unhappy with the internal conditions. We don't think there'd be a significant noise impact when you open the window. So it'll only happen when you burn your toast or you're painting, so once a month, maybe less than that. So we don't think the acoustic impact is important. And although not my speciality, because it's such a short duration activity, it's unlikely that there'd be any significant air quality effect as well during purge vent. So very rarely, I mean, I don't think we'd ever recommend sealed windows for acoustic reasons. We'd always say purge ventilation should be required, should be provided by open windows.
And on that air quality point, you traditionally only do it when the air quality inside is very, very extremely poor. So it's actually you're actually wanting to remove those pollutants, and it is such a short exposure time that you will then shut the window or shut the system once those pollutants have been removed.
Okay, thank you. In your view, who should be in control of the solution? Is it the architect? Collaboration requires a leader.
Everyone likes to be in control, but yeah, collaboration is key. I think setting out principles early is key. Deciding who coordinates that and what the drivers of the scheme are is probably going to determine who the leader is. So for instance, looking at this early on, when we are looking at massing, when we are looking at site layouts, when you're looking at okay, well, what is going to go on that noisier facade of this development? As Matt said, could we put the kind of residential portion on the scheme on a quieter area? All of that needs to be kind of a joint decision. We don't want to get conflicting reports the week before we go into planning, or at worst, post-planning, when we've got system designs that have been approved but won't work in practice and leave the team liable. As far as leadership, I think we all have a kind of responsibility to deliver homes that are suitable for now and the future.
I think at Cundall, though, we are looking to help lead this more and more in future, because we have that in-house. We have the acoustic skills, the air quality skills, the sustainability skills, and we have most of that knowledge. There are other factors, but we are aiming to lead this on lots of assessments at the moment. So,
okay, thank you.
Yeah, I'd say the architect has to lead as the design team leader on these things, where we quite often run into challenges are where people have got well advanced and developed ideas before we get all of the advice that can help the scheme on both develop well, and then you're trying to retrofit the design into a set of fixed ideas that people have. In terms of the combination of all of these factors, if we're looking at some mid or high-rise buildings, we're employing lots of these different technologies at different levels and different facades of the building, and getting involved at the earliest stages obviously allow us to bring that to bear at the most useful time. But yeah, I'd have the architect leading myself, and we'll help in every way we can.
Thank you. We've still got a few more to run through. So are we aware that building regulations will be looking at internal noise issues in tandem with overheating design in the future?
I know it's being looked at in the consultation for new building regs. I'm not sure if it's going to make the final version or not. If anyone does know better than me, I'd be really interested to find out. Though, so.
Yeah, from an overheating point of view, the future homes review is ongoing. That predominantly looked at energy, but there was an exercise undertaken where they kind of modelled sample overheating dwellings across the country, various typologies. How much they alluded to noise in that, I'm not sure. But items like the GLA are dictating that we undertake these overheating assessments, and their guidance documents refers to the ones that Matt has been co-author on, and the document he's previously discussed. So there is guidance out there, and teams are becoming more aware, and the consequences of not doing it are severe in use.
Okay. I wonder who you think is best placed to undertake the dynamic study which looks at acoustics, ventilation and overheating in one. Is it the acoustic consultant, the MEP consultant, the facade consultant, or is it better in a standalone appointment?
I think it needs to be balancing the acoustic issues with the overheating issues, and ventilation stuff probably needs to be a multidiscipline effort. Basically, there are very few people that they're experts in both of those, and that's where we'll work on the projects here at Cundall. We just work very, very closely with Ollie's team and Glyn's team to make sure all those different issues are looked at.
I think the first thing we do on a project is pick up the phone, be that internally, externally, whoever the parties are involved, and say, what are there any constraints placed on it from X, Y, and Z, acoustic, security, architectural? Is there a certain aspiration from the client to have certain amenity space, balconies? All of this is integrated. Trying to approach it as individual items will lead to conflict and a rush to get things right, if not beyond the point where they're already too wrong.
Okay, I realise we've just run slightly over, so we'll just pick these last couple of questions. So are there any thoughts on using noise cancelling technology to manage external noise through open windows?
There have been some studies done on noise cancelling windows, and they are a really good idea. And there was actually a newspaper article saying that noise was halved by a noise cancelling window, but technically when you halve the noise, you reduce it by 3 dB. So it's not quite as good as it sounds. So they can work, but the research I've seen shows it's not a significant reduction in noise, and it's probably the value compared to the reduction in noise you get at the moment probably isn't quite there.
Okay, thank you. We're seeing more air quality filter units for developments in poor AQ areas where an alternative clean air intake isn't possible. Do you have any thoughts on these, the types of pollutants they filter and their maintenance requirements? Not sure if that's one for us guys, or we can pass it on to Glyn, but if anyone's got any thoughts on that one.
So the key aspects on that filtration is that it's there to filter just the background ventilation. To actually comment on what it filters out and the purposes, I'd have to leave that to one of more specialist colleagues. But I know there are issues with occupant responsibility on changing those filters. If it is a kind of a landlord or a freeholder item, how can we position those filters so they can be accessed without going into the tenant demise? All kind of issues surrounding the filtration.
Yeah, and I think part of it's getting dealt with, rather than an individual building basis, on a citywide basis, driven by planning, with the push to have low emission vehicles and zero fossil fuel consumption on sites to reduce the level of pollutants in the local environment in built up areas. So it's that's where the bigger push comes, that will eventually avoid the need for individual residents to try and filter out their air pollutants coming into their residence.
And I suppose the challenge at the moment is designing buildings that work now, but in 10 or 15 years' time, if air pollution's significantly reduced, that filtration might not be needed. So we've got to incorporate both those factors. So.
Yeah, and we're doing that. We're introducing filter units that eventually can be dropped out as they're not needed, depending on the site. Yeah.
Okay. Do you see the inclusion of comfort cooling increasing in residential building design given the rise in global warming?
I've seen this question, and I've seen the next one saying, how the hell are we still ending up with resi blocks for full height glazing in city centre environments? And yeah, the building residences in temperate conditions existed thousands of years before we got anybody designed mechanical and comfort cooling systems. So there's plenty of good examples globally of how you design and build buildings to cope with not increasingly warm, but warm temperatures that there are. Yeah, limiting solar gain, being careful with orientation, use of thermal mass, all of these passive measures are what's always been available in the design of buildings. And I guess it becomes a little bit more complex when you start to design high-rise buildings. But given the two questions, yeah, we are seeing an increasing number of schemes being developed without comfort cooling, but without comfort cooling on day one, but with the provision to allow comfort cooling to be retrofitted should the need arise going forward. And that can impact on things like floor to ceiling heights, riser space provision to allow this to be done and designed so it can be fitted without having to rip the entire buildings apart. But we still see a push to design with full height glazing, particularly the more money you want to spend on your apartment. The closer you get to the top of the building and the more you're going to pay for your apartment, then it seems to be the glass area seems to be proportionate to that as well still. So even in current schemes we're designing, full height glazing is still a very desirable attribute for lots of certainly the reception and living areas.
One of the Ollie, one of the key key reasons I got involved in the overheating and noise research was a misunderstanding of this. So the new guidance will mean that some developments as a recommendation for cooling if noise impacts are really high. But one of the reasons I got involved was to avoid the flip side of that, where if the noise levels are very slightly over the currently prescribed levels, suddenly you have to install cooling, and we wanted to avoid that because it's obviously not the right solution, and it's getting the balance for the right buildings. So.
Yeah, and I think it's setting it up so that if those restrictions on window openings are removed, so hypothetically, let's say our streets are pedestrianised, especially in city centres, we're then removing that noise and potentially that air quality issues, that our buildings are easily adaptable, that we can switch off the air conditioning, we can remove it, and we can rely on openable windows. Obviously, there's a lot of ifs and buts, but that's how we're looking to future-proof scenarios where we are looking to develop on these blighted sites. There's also certain private sectors that have a market expectation for cooling, and so it's how we present that to a planning authority or a local authority in a way where we are giving occupant choice. They can either rely on open windows or their kind of active cooling system, and there's not too much you can do to tell people not to use their cooling. It's kind of the way it is.
Yep. Okay. What is your opinion on introduction of plantations, so trees, for example, when possible, to mitigate or reduce noise impact? This is a measure that could also contribute to the reduction of the risk of overheating.
In terms of noise, trees and bushes and plants and things don't often offer much sound insulation. So you'd have to have quite a deep set, thick bit of trees to reduce sound traveling through them, but they can absorb sound. So if you have green walls and things, less sound will reflect off the opposite building. So there is, externally, there is some option for that. Internally, it's unlikely, I think, that you'd have to have a significant amount of plants in your room to significantly reduce the noise, because they only really provide absorption. So. But externally, they can be used, and green walls are probably the most effective place.
Okay, and just the final. Sorry. Oh, sorry, Ollie, go on.
Yeah, just to add to that, we've seen a lot of research, predominantly around the office setting, where introducing internal biophilia plants actually makes people more willing to accept greater temperature ranges. So you're not actually changing the temperature in that space; you're just changing people's perception on what they feel comfortable in. It's really fascinating and slightly kind of, you have to get your mind around it, that the plants aren't actually doing anything, but they're providing comfort through kind of other means that mean people are more receptive for wider temperature ranges.
Okay, and we'll just do this final question before we sign off this morning. So how can we deal with access to MVHR in affordable dwellings managed by housing associations?
I'll go. So what we are often what we're often seeing is coordination of the ceiling plan. So can we put this, not only the ceiling but also the wall? Can we mount these so there's almost an access hatch from externally to allow those filters to be removed without disturbing or going around tenants and occupiers? The other point is, how can we just educate users if we can't do that? So look at saying your building will need this filter changed periodically every 6 months, and how can we aid that process? Because it's not natural, and people in their own homes often let things degrade a bit further than they would in a kind of professional setting.
There's a bit of a noise conflict here as well, actually. Quite often in a large development, you might place the more expensive market type properties on the quieter facade, so they might not need cooling, but they might get it because that's a desirable thing at that level of the market. Whereas in a more affordable home, people are quite reluctant to put cooling in. But if that affordable home's on the loudest facade, that might be the location that needs cooling the most to stop acoustic issues. So there's definitely a balance there, and in affordable homes, people are less keen to also pay the service costs that comes with. So there can be conflicts there with acoustics and cooling.
Perfect. Well, thank you very much. We've run slightly over, but there was just so many questions to get through. Thank you to everyone who's joined us this morning and to our speakers, Matt, Ollie and Thomas as well. We will be putting a recording of this on YouTube, so if you missed the beginning of it or had to dip out at any point, we will have the full recording on there. So we'll be sending that out shortly. So thank you, everyone, and enjoy the rest of your day.
Thank you, and hopefully see you at the next one. Yep.
See you. Thank you.
Bye.
Bye.